gentlemen, welcome back for another round. This is Mr. Doolin. I thank you for tuning in. Today what we're going to do is we're going to take a look at general equilibrium, and this is just kind of the general overlay of what equilibrium is all about and some of the things that we're going to see and use it for. All right, so first things first, let's define what and remind ourselves what equilibrium is, because hopefully you've seen and heard this term before this particular lecture, right? Remember, equilibrium exists when the rate of the forward reaction, rate is important there, right? The rate of the forward reaction is equal to the rate of the reverse reaction, and that's definitely a definition you want to get down, all right? So equilibrium exists when the rate of the forward reaction is equal to the rate of the reverse reaction. So since we're talking about rate here, I'll go ahead and make a concentration versus time graph. Now notice our reactants should decrease in concentration. And then let me switch colors here. Our products should increase in concentration. So I'll make that products there. And I'll make the red line here reactants. So we have to get this understanding and wrap our head around what does it mean that the rate of the forward reaction is equal to the rate of the reverse reaction. All right? Well, what that means is that for every amount of product that disappears, right, for every amount of reactant that disappears, right, to make product, we'll have some product disappear to make a reactant. And so essentially, it's like me giving you $20 and you giving me $20, right? Nothing actually happened. We exchanged money, right? So I guess you could say something did happen, but there was no net change, all right? And so what we need to be able to do is figure out where in this graph is equilibrium. At what point is equilibrium actually established? Well, it's when this product and reactant concentrations become constant, all right? And so at equilibrium, my product concentrations and my reactant concentrations are not changing. The reaction is still occurring. I still have a forward reaction occurring. I still have a reverse reaction occurring, but they're occurring at the same rate. And so remember, when we draw these concentration versus time graphs as well, we need to make them stoichiometrically correct. And so this is just a general graph here, products and reactants, but we need to understand, right, those coefficients in my balanced chemical equation do affect individual rates and will affect how fast and slow something appears or disappears, all right? Because that's really what this graph is. It's a concentration versus a time graph, which is a rate, right? So what we do is we understand that when these things level out here, right, when this becomes linear, that's when my equilibrium is established. That's a point you will be able to need to be able to identify on the graph. But when those concentrations become constant, we have that constant ratio of product concentrations to reactant concentrations. And what we can do with that is we can make an equilibrium expression. Now the equilibrium expression is equal to some constant, because remember that product to reactant ratio is constant, and we're going to call that our equilibrium constant, is equal to the concentration of the products raised to some power over the concentration of the reactants raised to some other power, right? So where do those powers come from? Well, they're coefficients in the particular reaction. So if I had just generally 2A plus 3B gives me C plus, let's call it 4D. What would this expression look like? Well, it'd be a capital K, right? And that's equal to, and that's different than my rate constant for rates, right? This is capital K. That's equilibrium constant. So I'd have products, which is C, concentration brackets, right? And then D raised to the fourth power, concentration of A squared, concentration of B cubed, right? And so remember my rules here, that when I'm writing my equilibrium expressions, products over reactants, coefficients become exponents, and I leave out solids and liquids. So I leave out those pure substances. I'm only concerned with things that are actually going to change concentration over the course of the reaction. All right? And solids and liquids, pure substances, do not change concentrations. All right, and so you can imagine this singular instance where I'm at equilibrium. It doesn't occur all that often, and so what we use here is something called the reaction quotient, and I'm going to abbreviate that as a Q. And my reaction quotient, essentially what I need you to understand is this is what we're going to work with 99% of the time, is we're going to call everything Q, all right? And then only when our math tells us this ratio of products over reactants is equal to a very specific number, can we say we are at equilibrium. So it's when Q equals K, we are at equilibrium. In all other instances, we are not at equilibrium. So if Q is greater than K or Q is less than K, we're not at equilibrium. And what we can do is we can use that ratio of what is known to be equilibrium, that ratio of products over reactants, to kind of lead us and guide us and say, well, which direction will this reaction go given these particular conditions? All right, which way will it go given the particular conditions? And that's when Q becomes really, really useful. It allows us to be able to manipulate these kinds of reactions. It allows us to predict, hey, given these particular situations or circumstances, where's my reaction going to go? Is it going to be going primarily forward or primarily in the reverse reaction, right? The other thing that we definitely need to make sure that we understand is that going back over here to this equation, if K is greater than 1, that means my products are actually favored, right? Because products over reactants is bigger than 1, that means I have more products than I do reactants. So K greater than 1, products are favored. K less than 1, I don't get very many products formed. I have a lot of reactants remaining. I've got K less than 1. That is actually going to mean my reactants are favored. And you will definitely want to be just like secondhand to knowing, hey, greater than 1, my reaction is primarily going forward. I'm going to have products produced. K less than 1, not really. My reverse reaction's favored. Not going to have a whole lot of products produced in there. All right? Whew. Okay, that's a lot. Let's keep on going. All right, and so now what I'm going to do is I'm not trying to scare you here, but there's a lot of different equilibrium constants that we will actually deal with here in AP Chemistry. The first one that you'll see come along is actually Kc. And what Kc is, it's the equilibrium constant that is based on concentrations. So get that down. Kc is your equilibrium that's based on concentrations. The next one that we will see and deal with is called Kp. Well, Kp is based on pressures. And so what has to be true in order for us to use a Kp is that every substance that would appear in the equilibrium expression must be in its gas phase. And so go back to our example earlier. If, let's say, this particular reaction was all gas phase, so A, B, C, and D was all gas, what would my Kp expression look like? Well, it's a little bit different than using concentration brackets because now I use a capital P to denote pressure, and I would have P to the C, subscript to denote that this is pressure of C, and then I would have the pressure of D. I still do the coefficients become exponents. It's still products over reactants, so it's very similar to writing a Kc expression. And then I've got Pa, this would be squared, and then Pb, this would be cubed. And notice it doesn't matter if I put the exponents inside the parentheses or outside the parentheses as long as it's attached to the correct pressure. All right? And so this is what a Kp expression would look like, is I would be using capital P's to denote that I'm using pressures. And notice with this one, we have to have everything in pressures. I can't have anything in concentrations here. All right, so big difference between Kc and Kp is that Kp, every substance that goes in the expression has to be in its gas phase. For Kc, I can have either or, I can have a mix of things, but it all has to be concentrations, because I can even have a concentration of a gas, right? Because I've got moles divided by liters to give me my concentration. All right, the next one that we'll take a look at is actually called Ksp. Now, Ksp, the Sp actually stands for solubility product, and we'll get more into this later, but essentially what a Ksp is it's talking about if I have some solid, how much of it would actually, and make these aqueous, B minus, and that's aqueous as well, how much would actually dissolve? And so notice with this, now I've got Ksp, and I've got concentration of A times the concentration of B, the way my reaction's written up here. Notice I'll exclude my reactant every single time because my reactant is always a solid that is dissolving. All right? And so with Ksp, we'll never have our reactants down there at the bottom. It'll always just be products multiplied and then raised to the particular exponent. So the equilibrium expression writing, the rules are the same no matter what particular type of K I'm dealing with. All right? It's products over reactants, coefficients become exponents, and I'm going to exclude solids and liquids. So that's true every single time. All right, the next one that I'll take a look at is actually called Ka, and this is what's called my acid dissociation constant. And what happens here is when I have a particular acid, and in this particular case, how much of it actually dissociates to give me my hydrogen ion. All right, and we will definitely cover, we have a whole unit of Ka and its counterpart here, Kb, which is now the base dissociation constant. And so in this particular case, how likely is my base to pick up a proton, right? And again, these have equilibrium expressions on them as well. And then the very last one that we'll want to be familiar with is called Kw. It is the water dissociation constant. It is actually a constant number. It's 1e negative 14, and it describes the likelihood of a water molecule to dissociate into H plus OH minus. All right? Okay, ladies and gentlemen, this is it. These are all the equilibriums that we're going to cover, the constants that we'll cover over the next couple of units. But primarily in this one that we're in, we'll be dealing with these three here, Ka, Kb, Kw. We'll get to that when we get to acids and bases, but I wanted to introduce them here just to let you know, hey, there are other types of equilibrium. And equilibrium, man, generally speaking, they can refer to it as KEQ, right? And that's just general equilibrium. And if they give you KEQ, you can use concentration, you can use pressure, all right, whatever you want to use there, okay? All right, ladies and gentlemen, that was a lot. If you had some questions, I hope you got them down. I'll see you in tutorials for those. Otherwise, I will see you in class.